All right, today we're going to continue looking at classification tree that we developed last class and how to interpret the tree, and very important question, is this tree accurate, good enough, or not? Okay, but first things first, go to the Scholar, to the web page of our course, and over there I have posted the R script that we developed in the previous class. So in case your script wasn't working, okay, it's working, right? All right, so go to data files. That's where I'm going to post all the files that we will look at this semester. So here is Titanic data set, and the script that I posted last time was this one, Titanic classification tree R script. So the way, oh, by the way, which browser we are not using? Internet Explorer, because what I found is it's not working for whatever reason in Internet Explorer. When you double click on the downloaded file, it just doesn't open in RStudio. I don't know why. So click on the script, it will download on your machine, and then after double clicking, it should bring up RStudio, just like that, with the script in there. Okay. I suppose I need to make it bigger, right? Okay, magnifier. All right. Okay, so a couple of things that I want to point out, okay, before we reproduce the same tree again. Last class, what we did was a reminder, right, what this whole problem is all about. Pretty useless, what we're doing, okay, but it illustrates nicely the idea of classification tree. So we're trying to predict, out of all passengers who traveled on Titanic, who will die and who will survive, right? That is our target, the column called survive, with a capital S. All other columns we're using as predictors, and there are three of them, right? There is age, sex, and there is class, what passengers traveled on Titanic, okay? Now, what we did in the previous class was we just created a tree model and showed it, right, displayed it. Now, for that, we were required to bring in external library. Remember, we discussed that several times. This is one of the reasons why R is so popular and powerful. Because if R cannot do something by itself, natively, you can always download an external library, install it, and then use that, right? So, we downloaded two libraries last class. This one right here, install .packages rpart. Rpart stands for recursive partitioning, right? So it's repeatedly splitting data sets further and further and further until either there are no more splits, no more variables to split, I'm sorry, or you split it good enough. In other words, it's almost pure. The resulting two subsets are almost pure, and you cannot improve them by splitting any further, okay? So, we installed this last time, right, on our computers. We ran this line, so I don't really need this line anymore. It's already installed on the machine. So, I'm going to delete that line altogether. And another thing that we installed was right here, right, install package rpart plot, because that package will allow us to show the tree, right? So, again, I already ran these two lines, right? If you didn't run them on your machine, then you need to leave them in, okay? But I did run them on my machine, so I'm going to delete this thing. Package is already installed. Well, because you know, when you're using Excel, do you install it every time when you use Excel? No. Same thing here. You install the package; it's already here. Yeah. Only sometimes, for whatever reason, what I found is packages that were installed before, they kind of disappear, right? So you try to call rpart. That happened on the exam a couple of times. And it says there is no such thing. Then you have to run the installation, right? And you have to either write this line, install, or, we discussed that, maybe you forgot, I don't know, we'll see. You go to the packages, right? So this window, this part of the window, you go to the packages, you click on the button install, and here you type the name of the package, rpart. And then you click install button, it does installation. Same thing, okay? You can do it through the typing the command, or you can go through this button install. The result is the same, okay? So since I installed that previous time on my machine, I don't need really install. All I need to do is load the library rpart, this line right here, and after that load the library rpart.plot. Okay. One thing that I want to show you is kind of a new thing. It's not a trick. It's more like a shorthand way of doing things. Let's execute this script line by line. I mean, I can do it in one shot, right? I can select the whole thing, click the run button, and it will run the entire script. Okay. And I'm going to do it line by line. So first line right here, Titanic data. Control Enter. What I did is I read the CSV file, right? Next one, well, we showed the structure of the data, and it told us that there are 2201 records, and there are 4 variables, right? Survived, class, age, and sex. Okay, that's good. Next one is I'm going to bring in, load the library into the active memory, right? Library rpart. And when I do that, it shows me the red warning. It says warning package rpart was built under later version of R, so may or may not work. It's up to you to use it or not. I'm fine with that. Okay, the next one, what we did in the previous class, this line right here. Okay, what this line says basically is go ahead and create for me through the recursive partitioning rpart classification model, right? And I recorded the result, the model itself, in this really long variable, which I called Titanic classification tree model with underscores, right? So, and what I told you is how to interpret that portion when you're calling the function. Basically, this portion says that my target is going to be the variable survive. And my predictors, that's what tilde here basically says. Survive versus these variables, right? Predictors are age, and sex, and class. And I told you that plus sign is not actually an addition, right? It's kind of a word and. So I'm saying that my predictors are going to be age, and sex, and class. Okay? So there is no addition going on. All right? And then after that, I have to tell which data set to use. That's Titanic data, right? And then I told you that we need to specify the method, okay? Because the function rpart can build 2 types of models, right? It can build classification models, just like this one, and it can build regression models. Okay, we're going to discuss that later, next week probably. Okay. All right. So here's the trick that I want to show you. Right. So this data file was fairly simple. There were only 3 predictors. Well, later this semester we're going to look at the files with a lot of predictors. Okay. So if I don't want to type predictor 1 plus predictor 2 plus predictor 3 plus, etc., right? Here's what I can do. Instead of typing variable plus variable plus variable, I can go ahead and say dot. And that's it. Question. Dot basically means all of them. Okay? So, what the rpart function will do is it will say, okay, there are 4 variables, 4 columns in the file. One of them survived, is the target. Everything else is a predictor. Okay? So instead of listing every single column, I can just go ahead and say dot, and that would be enough. Okay? That's a shorthand way of running model when you have a lot of predictors. So go ahead and run this line. Well, there is nothing going on, right? It doesn't show us anything, which is fine. But yeah, that's the way basically how you can say use all variables instead of typing them. Okay? And by the way, just for the future reference, also, if I want to exclude certain variables, like for example, let's say I want to exclude variable class. How can I do it? I can go ahead and say dot means everything, but remove the variable class. Minus class, exactly. Minus class. Yep. So, dot minus class means all variables, but remove the class. So it will use 2 predictors, age and sex, okay? I'm not going to do it, but I'm just showing that so that you know for the future references that you can manipulate which variables to take into the model or exclude from the model like that, okay? So, I got my model, and now I need to show it, right? So I'm going to run. That is done by another library, rpart.plot. So again, I removed the install piece, right? Because I kind of assumed that last time I installed it, it's still here. So I'm going to load the library. It gives me the same warning, which is fine. And then the next line, I'm going to show my tree. And there it is. Okay? So, how are we doing so far? Yay? Uh-oh. Any problems? Everybody got the tree? All right. So let's take a look at what is shown to us. Okay? How to interpret this output. All right. Well, first of all, to review, last class we discussed that as the tree grows, well, the reason why it's called recursive partitioning is we keep splitting the resulting subsets further and further and further until either we run out of variables or there are no more good splits, right? Or we achieve perfect split, which gives us pure final resulting nodes, okay? So this node at the top represents my entire data set. That's where everything starts. 2201 observations, everything that was related to Titanic data set, okay? That's why it says 100%. 100% of the data, okay? And you can see that each one of these nodes also shows a number, right? So this one is 0.32. What does this number represent? This number represents the fraction of all observations, proportion of all observations that are classified in that set as a yes, okay? Or as a 1, right? We discussed that yes and no corresponds really to 1 and 0, right? So the percentage represents the fraction of all observations that are classified as a yes. So in the entire data set, and what do we mean here, by the way, by yes? Yes what? Yes? No, it's not about default, it's about survival, right? Yes, survive, right? So in our data set, 32% of all passengers survived the Titanic catastrophe, right? So therefore, 68 did not survive, okay? All right, so we're going to get to the no and yes a little bit later, right? Now, the very first variable that our part function decided that it's the best split out of all things, right? We tried to split on 3 different variables, right? Tried to split on age, sex, and class, and it said the best result is achieved in terms of pureness, right, of the resulting subset. The best result is achieved if we first split on sex, male, female. Well, right here, here is a helping sort of picture for you, right? If the answer is yes, you go to the left. If the answer is no, you go to the right, okay? So this node right here represents what? Male, right? This node contains all. Male yes goes this way. So this is all males, right? This is all females. So right here it says that 79% of all records were male, and therefore 21% female. Among the male, what is the percentage of survivors? 21, right? This number represents proportion of yes or 1 answers, right? So 21% of all males survive. How about females? 73% of females survive, right? And then later, it says, okay, let's try to split all males node even further. So it decides that the best split is going to happen on whether or not they're adult. So going on the left means what? Adult equals, same idea as here. Sex equals male. Yes goes to the left, no goes to the right. Age equals adult. Yes to the left, no to the right. So on the left, what do I have? Adult, yes, adults, right? On the right, I have adults, no, that's children, right? Okay, and then it decides that there is no really improvement in splitting this node further. So this becomes a terminal node, right? And this one is internal node or decision node. It splits further. If the node splits, it's not the final destination, so to speak. Split keeps going, okay? But once the algorithm decided that, hey, there is no more splitting, for whatever reason, right? Either we ran out of variables to split, or it will not give me a better result at the end if I keep splitting. This is where everything stops. This is called terminal nodes. Terminal nodes are important for us because they basically give us the intended classification. Okay, so I know that it doesn't make much sense right now. It will in about 10 minutes and 15 seconds. Okay, all right. So let's see. So over here, let's have some practice. So this node right here, yes, 1.01%. What type of passengers does it represent? Tell me, what's the typical profile for that node? Child, not in third class, and male, right? So going here, it's a male. Going over there, adult means no, right? So therefore, it's a child. And from here, we go to the right. That means no. Class equals third. Well, that means that it's either first class or second class or a crew. Well, I doubt there were any children in the crew on Titanic, so therefore it's probably first or second class, right? Okay. Now, let's get down to this issue. What these no's and yeses represent. Very important thing. So important, I'm going to write it down, okay? Cutoff value. Cutoff value for classification, default. Let me put a word default here. Default cutoff value for classification is 0.5. Okay. This is the default cutoff value that is used by classification tree. Later, in about 4 weeks or so, in this class, we're going to discuss logistic regression. Same thing, okay? All models that are classification models, just like this one, classification tree, are using the default cutoff value for classification purposes equal to 0.5. What does that mean? Here's what it means, okay? Let's take a look. I'm looking at the terminal node, okay? So I'm not looking at the root node, this top node, which is called root. I'm not looking at any internal nodes that splits further, this one, or this one. All I'm doing is I'm looking at the bottom of the tree, terminal node, okay? So let's take a look at this node, for example. What type of people end up in this node? Tell me. On the far left. Male adults, right? So these male adults, first of all, what's this 76% mean? That means that it's the percentage of the entire data set, right? 76%. So if you look across the bottom, 76% plus 2, that's 78, plus 1, that's 79, plus 9, that's 88, plus 12, that's 100, right? 100%, that's how they're distributed, right? 76% of all passengers were males, adults, right? What percentage among them survived? 0.2. 20% of them survived. What percentage died? 80%. Which one is higher than 0.5? 0.2 or 0.8? 0.8. Therefore, what classification tree says is this. The default is 0.5. Whichever is higher than 0.5, that's how I'm going to classify this entire terminal node. Okay? So the percentage which is highest is for no, did not survive, right? 0.8. Therefore, this entire node is classified as non-survivors. Okay? So all people who resulted in this terminal node right here, 80% of them died, so therefore this entire node is classified as people who did not survive. Whichever one is higher than 0.5, that's the classification that we assign to the terminal node. That's the rule. That's by default, okay? We can manipulate that, and later in the semester I'll show you how to do it. But default classification is whichever is higher than 0.5, that's how we classify it, okay? So let's take a look at this one on the far right. Tell me what kind of people end up in the far right node. Female, third class? Non-third class, right? Because third class yes goes this way, third class no goes on the right. What does that mean? Third class no. Crew, first or second, right? Okay. And there are 12% of passengers like that on Titanic, right? Among them, what's the percentage of survivors? 0.93. Is that a big surprise why this whole thing is classified as a yes? Because 0.93 is higher than 1, right? Oh, higher than 0.5. So therefore, that's how we classify this entire node, okay? Even though 7% of them died, right? But everybody who ended up in this node are classified. That's what our model does, okay? It's not 100% accurate, but that's what our model does. As long as it sees a female who traveled non-third class, it says, yep, regardless of their adult or child, female non-third class. Survived equals 1. Yes. That's how our model behaves, okay? All right. So let me show you an example how we can use this classification tree. Let's say I have a child, male child, traveling in the second class. Will they survive, or will they? What our model will predict? Okay, for them, male child traveling second class. What would be their classification according to our model? They will survive, right? Because male, yes, goes this way. Adult, yes, goes this way, but this is a child, so we go on the right. We go to this node, and this one says, is it a third class? No, it's a second class, so go this way. So we arrive to this node, and look at that. There's only 1% of passengers like that among all of them, but the survival rate for them was 100%. So this is a pure node, right? The only one, actually. Do you agree? Pure node, again, reminder, is the one that has all yeses, 0 no's, or other way around. 0 yeses, all no's, right? This is as pure as it gets, right? And that's the only pure node that I have in my entire tree, right? All male children traveling in non-third class, all of them survive. That's the only pure node, okay? All right. Any questions about how to interpret the classification tree? Uh-huh. Oh, the very top one? Very top one, we don't see. When it comes to classification of different individual observations, we look at only at the bottom. But let's take a look at why these yeses and no's are in these nodes, right? So, the tree basically does it formal, right? In the entire class, 100% observations, what's 0.32? Among all people on Titanic, survivors were 32%. Non-survivors, 68, right? Which one is higher than 0.5? 68. Therefore, if we forget about everything else, everybody on Titanic should be classified as non-survivors because 68% of them died, and that's higher than 0.5, right? But now we start splitting things up, right? So in the male, here, males, right? 21% of them survived, 79% of them died. That's why, because 79% is higher than 50.5, right? That's why this node is classified as a node. And males, females, right? 73% of them survived. That's why this one says yes, okay? But really, we don't pay any attention to these nodes because this is not the final destination, right? There is more split going on. So the only thing that we should pay attention to are nodes at the bottom, okay? The terminal nodes, all right? So these yeses and no's that we see in the internal node or in the root node, we don't really care about that. All we're looking at is at the bottom of the tree, the terminal nodes. That's how we classify observations, okay? Now let me show you actually how the classification is done, okay? Let's kind of do it by writing some code, okay? So it's actually kind of a good moment to talk about accuracy. Do you realize at that point that this tree is not 100% accurate? Said somebody somewhat reluctantly. Okay, let me illustrate that this is right. Okay, the tree is not 100% accurate. All the males, all the adult males are classified as what? Non-survivors, right? In actuality, 20% of them did survive, right? So therefore, in 80% of all these observations, we would be right. But in 20% of the cases, people who did survive, we would still tell that they will not survive. That's what our model will tell, right? So it will be an error, right? Misclassification error. So our model is not 100% accurate. In fact, let me tell you, none of the models that we're going to build this semester are going to be 100% accurate. Okay, the question of like how far off are we? Okay, we should have some sort of the idea or measure how accurate is our model. Is it a good model or is it pretty bad model, because it misses a lot of cases. Okay, so let's kind of start talking about misclassification. All right, so I'm going to bring up this. All right, so here are the possible outcomes. Okay, well, actually, you know what? Even before we do that, I promised you to show how it happens in the software, right? Okay, hold on. All right. So what I'm going to do next is I will use my tree to make a bunch of predictions. Okay, true or false about each passenger. I know what really happened. They survived or not. Yes, I do know, right? It's in the column survived, right? Each observation, each record says yes or no. So I know what actually happened. And I want to compare that against what my model believes happened. So here is how we use our model. I'm going to run the model, and for each 2201 observations, I'm going to ask the model to predict, will that person survive or will they die? Okay? This is done by using a very universal function built into R, which is called, not surprisingly, predict. Okay? So, I promised you to document everything that I'm doing, right? So, generate predictions by the classification tree model. Okay? So I'm going to, just like everything else, what I do, every time I create something new, I record that into object, into a variable, right? So I'm going to say Titanic underscore classification underscore prediction. So for each passenger, I'm going to predict what my model thinks. Did they survive or did they die, right? Not what actually happened, what my model says, okay? And I told you that this is done by the function predict, okay? And predict, in this case, will take three parameters. First of all, which model do I use? Well, the one that I just built, right? And that would be Titanic. Whoops, Titanic. As I start typing, it says, yeah, there's a bunch of stuff that starts with Titanic. Okay, classification tree model, this one, right? Bam. Okay, next one. Hold on. Next one. I have to say comma. I have to tell which data to use. Actually, strictly speaking, I can just skip this thing. It will use the same data, Titanic underscore data by default, but let me be meticulous about that, okay? I'm going to say new data. Really, it's my old data. What's my old data is called? Titanic data. And also, remember, I told you that we can have either classification tree or regression tree, right? This one is classification. So therefore, what I need is yes, no predictions, right? So therefore, here I'm going to say, and this is what's different, okay? In the function, what we used to create our part, we said method equals class. This function uses different name of the parameter type, okay? That's probably something you should put on your cheat sheet for the next week's exam, okay? I don't necessarily want you to memorize this stuff. Write it down, okay, so that you can consult with your cheat sheet during the exam. So type equals class, classification, okay? Tree. All right, so let's go ahead and run this line. It should have no visual impact, just basically run the command. And now, I think I have all predictions, okay? Let's kind of look at them, shall we? How do I look inside the variable? I just ask R to print it for me, right? So I'm going to say, show me Titanic predictions. This thing that I just created. Bam. Oh my God, look at that. Just a bunch of numbers and yeses and nos. What do you think numbers represent? 1, 2, 3, 4, 5. Record, right? Record first, second, etc., right? Let's take a look at the first record. The model predicted that the first record did not survive, right? Okay. Well, let's take a look if that's true or not. So here's what I'm going to do. Let's see the actual record number 1 in Titanic. In fact, I'm going to show all the records in Titanic data. Titanic underscore data, please show me all the records. Let's scroll up till we see number 1, right? So first record. Now, for the record, pun intended, okay, the actual value was survived, yes, right? So passenger number 1 actually did survive, correct? Because that's what my data says right there. First one did survive. What did my model say? My model said no. Is that a good thing? My model made a boo-boo, right? It's an error, right? Should have been yes, but it was a no. But let's see how that no came up, right? So, first record was male, adult, first class, correct? Well, let's travel along our tree. Where do I go from the root? To the left, because it was a male, right? Where do I go from the second one? To the left, because it was an adult, right? And what do we see? All of them are classified as a no. That's what my model said. So in actuality, that person was a survivor, right? But the model said no, because you ended up in this bad company where 80% of people died, therefore all of them were classifying as a non-survivors, right? Well, let's look at another example with a better outcome. Let's take a look at prediction number. Oh, I cheated, right? I looked them up before the class. So 220. Observation number 220. Where is that? Right there. What did our model say? 220 did survive, right? Okay, well, let's see if that's truly the case. Who is number 220? I'm going to scroll. 220 right there is, they did survive, so our model predicted that correctly. But that was a female, adult, first class, right? Okay, so starting from the root tree, where do I go? To the right, because it's a female. Over here, class equals third. Yes? No, it was a first class female. So therefore, we go to the left, and what do you know? 93% of them did survive, so that's how they're all classified. Okay? Make sense? So again, our model is not perfect. It's not 100% accurate. It does make errors. Okay? All models that you will ever build in your life, if this will be your future, area of expertise in your future career, 100% of your models will have errors in them. Okay? The question is, how do you build an error with less? How do you build a model with less errors? That's pretty much the big question. Okay? But let me show you how do we identify, how do we calculate the model accuracy, performance. So for that, let me switch back to this beautiful drawing capability right here. Okay? So, generally speaking, there are 4 possible outcomes. Okay? So I'm going to say, oh God, what actually happened. Actual outcome, right? And one more thing that I want to point out. Every time when RStudio/R wants to list the categorical variable, such as yes, no, it does it alphabetically. Okay? So therefore, it will between yes and no, which will come first? No, because it's N, and yes, because it's Y, will come second. Okay? So actual outcomes can be no, they didn't survive, and yes, they did survive. Okay? So these are possible outcomes. Yeah. All right. At the same time, I'm going to plot what my model actually predicted. Okay? So over here, I'm going to say what my model predicted. And predicted again can be of 2 types, right? My model can predict that they didn't survive, or my model can predict that they did survive. Okay. Now, ladies and gentlemen, tell me, if my model predicted they didn't survive, and they actually didn't survive, is that the right outcome? Yes. So therefore, we're going to call them TN. T stands for true, N stands for negative. True negatives. Okay? So things that are no, and my model predicted them correctly. Okay? What's another good outcome from my model? Tell me. yes and yes, right? My model predicted that somebody survived, and they actually did survive. This we're going to call TP. P stands for positives, right? True positives. So I want my true positives and true negatives to be as high as possible, right? Things that I don't predict correctly, my model, that is, right, are off diagonal, right? So this one, when it's predicted yes, but in actuality it's a no, we're going to call false positives, right? Because our model predicted it's a positive yes, but it's a false, right? Right? This is false positives, FP. Because model says it's a yes, so it's a positive, right? But in actuality it's a no, it's a negative. So it's a false positive, really. Okay? My model says positive, but that's not true, right? And this one is going to be false negative. All right? So obviously, the more false positives and more false negatives I have, the worse my model, right? I want to build a model that has as many, preferably all of them, 100%, right? 100% either true positives or true negatives. And ideal case would be if your false negatives and false positives are zeros, right? Nothing is incorrect. Everything is predicted as it should be, right? So therefore, ladies and gentlemen, allow me to introduce you to two measures of accuracy that are closely related. One of them is called literally accuracy. Accuracy, okay? So I'm going to write down number n over here. N would be total number of cases in the entire file. In our case, it's going to be 20 to 101 passages, okay? So accuracy is simply how many correct classifications I have out of total. So in other words, true negatives, this is correct, right? And true positive, this is also correct, out of what I have in total. Or alternatively, I can write it like this. True negatives plus true positives, okay, divided by, my total is comprised of all four of them, right? True negatives, true positives, false negatives, and false positives, right? That's accuracy. It gives you quite literally percentage of cases out of all cases, right? What percentage was classified correctly, either yes or no. True positive means true yeses, right? They were yeses, and our model classified them, picked them up correctly. If there are no's, then model should pick them up correctly as well, and that's true negatives, right? So accuracy. Well, related to accuracy is something that's called using, I like the term, I don't like how long it is, okay? It's called misclassification rate. Okay, misclassification rate. So these are all things that are classified incorrectly, not just things, percentage rate, okay? So I classified incorrectly all false positives and all false negatives. Is that right? That's where I made, my model made a mistake, right? It should have been positives, but it was classified as no. It should have been negatives, it classified as yes. So this is where it messed up, right? And divided by n. Or, again, if I write it down as a formula, it's going to be, okay, true negatives. It's going to be false positives plus false negatives divided by, it keeps moving, divided by true negatives plus true positives plus false negatives plus false positives, okay? Now let me ask you this question. What will happen if I add together, let's see, accuracy and misclassification rate? 100%, right? Percentage of things that I got correctly plus percentage of things that I got incorrectly should be everything, should be 100%, right? So therefore, I'm going to write over here, accuracy, I'm going to abbreviate, accuracy plus misclassification rate should be 100%, right? So therefore, they are related, really, okay? The more accurate the model becomes, the less misclassification rate, and vice versa, okay? Well, ladies and gentlemen, in the time remaining, which is quickly running out, let's take a look how we're doing, how our model is doing, okay? All right, so I got myself predictions, right? Let me erase all that stuff, because it's not really relevant. I got myself predictions by the model, right? I even call them Titanic classification predictions. And I know that I have the real thing, right? What actually happened. Where is that recorded? Tell me. Where can I find the actual survived yes, no? Inside my Titanic data, $, column called survived, right? Remember, that's how we address variables in a file, right? Data name, $, variable name, right? We talked about that. So what I'm going to do, ladies and gentlemen, is I'm going to create crosstab. Remember, we did crosstab about a couple of weeks ago. One of my variables in the crosstab is going to be what my model predicted, yes or no. Another variable is going to be what actually happened, yes or no. So we're going to do it using the function crosstab table, right? Cross table. Oh my God! As I start typing, I can't find the function cross table. Why? What is going on? I have to install what? Remember what did we use? Package, what's the name of the package? Gmodels, right? But do I need to install it? Hopefully not. I hope that 2 weeks ago when I installed it, it's still here. So I need to load the package in the memory, right? So I'm going to say library Gmodels, right? Please bring to me the library Gmodels. And thank God it's here. It's installed, right? So I'm going to put a comment quickly, right? Load Gmodels library to use cross table function. And now, yeah, if it's not on your machine, which is possible, I don't know why, then go ahead and quickly install it. Okay, you can go through packages right here, right? Just click on packages, install button, type Gmodels, click OK, install, and that is there. The next thing you need to do is load it, okay? So, but if you have it on your machine, then go ahead and load it, right? Just like that. And the next thing I'm going to do is create a, okay, let me tell you something else, all right? This type of confusion matrix, this type of crosstab is called confusion matrix, okay? So when I'm creating a crosstab between the actual categorical variable versus what's predicted for this categorical variable, it is called confusion matrix, okay? Let me write that down. Confusion matrix. Okay? So this is confusion matrix. Official term. Alright, so I'm going to create, the reason why I discussed that is I want to put down a comment. Create a confusion matrix for classification tree model. Okay? So all I do really is I say cross table. Oh, look at that. Now it's there. Magic, right? I just loaded Gmodels library and there it is. So I'm going to use the function cross table. And I'm going to cross two variables. Predicted, yes, no, versus actual, yes, no, right? Predicted, I know how they're called, right? This is how it's called. It's a really long name. I'm going to say Titanic classification predictions, right, comma. And what's the other one we just discussed? It's located in file, what file? In the data, Titanic data, right? Titanic data. And I have to reference specific column which is called survived, right? And I do that with the $, right? So I put the $, and pick survived, capital S. Don't forget that R is case sensitive. It will not forgive you if you forget the capital letter, all right? And just hit Control Enter, and there is your confusion matrix, ladies and gentlemen. How do you like that method? Okay? All right, so we still have about 3 to 4 minutes remaining. Any questions what we just did here? Sure. Any questions? concerns, complaints, sarcastic comments? Okay. All right, so looking at this confusion matrix, tell me, what is my true positive? What's the count of true positive cases? 270. True negatives? 1470. False positives? 20? Yeah, 20. False negatives? 441. Can I calculate the accuracy? I believe I can. Let's go ahead and do that, okay? So, let's do that. I'm going to calculate the accuracy first. What's total number of cases? 2,201, right? That's my true positives, true negatives, false positive, false negatives, everything, right? Oh, I forgot. You tell me. 1470 is true negatives, and true positives is what? 270? 270. So therefore, we're looking at 1740, right? Divided by 2201. Can anybody quickly calculate this thing? I don't want to bring Excel. It'll take way precious time. I believe it should be around 79%. 79.79. So, what does that tell you? That tells you that 79% of all of my records in the file were classified by the model correctly. That's accuracy. What percentage of them was misclassified, if you would have to guess? 21%, right? So let's formally write it down, right? Misclassification rate is going to be, again, out of 2201, right? Oh God, what were they? Let's see, 20 false positives, 441 false negatives, right? So 20 plus 441, or in other words, 461 out of 2201, and that should give you, check my calculations if you don't trust me, 21%, okay? So therefore, question is that a good thing or is it a bad thing? What do you think? It's pretty good, right? It's not perfect, right? I still miss 21% of the cases. So in a sense, out of every, let's say, 10 passengers, right, I miss 2, right, on average. Or out of 100 passengers, I incorrectly classified 21 passengers, but 79 are classified correctly. If I would be doing it by flipping a coin, in what percentage of cases I would be right? 50-50, right? So this model is certainly better than just flipping a coin, right? Flipping a coin, you will miss half of them and you will correctly do another half, right? This one says, okay, if you're a little bit more smart about that and if you follow the tree, you will not get all of them right. 21% you will still screw up, but in 79% of the cases, you're going to be just fine, okay? All right, I think we're done for today.